let's jump in to something very, very general about the universe and try to come up in the end with an actual mathematical equation to describe it. Let's take something very ubiquitous like motion. There's motion everywhere. I'm moving, my mouth is moving, your head's maybe moving, your eyes are moving, there's wind blowing, there's boats moving out over there, there's a lot of things moving. Motion is all over, okay? All through there's things moving in your body, there's blood circulating and so on. What are some of the properties that you might want to study about motion? So the first step, remember, is you're looking at phenomena and you want to try to generalize as much as possible. So I don't say, let me study how my hand moves. And I don't say, let's study how a boat moves. And I'm not saying, let's study how the wind moves. What I'm studying is movement. So I've extracted out from many, many different phenomena one thing that's fundamental to them all, motion. Now, what is it about motion that I might want to study? Or what is it about motion that I might notice? Speed, okay. Okay, what does energy mean? Okay, so the power to create movement. So does movement have the power to create movement? Or you're saying, go on.
No, the energy has the power to create.
The energy of what? Okay, but let's say we're seeing something moving. You're saying there's something about energy, but no, like no. Okay. Okay, so something made it move. So when something moves, usually, well, we don't know. Does everything that moves? Did everything that moved have something that made it move?
Yeah.
Yes. No. Okay. What's the yes? Does it? How do you know?
You have to have an energy to move. You have to have a push or a force.
Is there anything that moves without being pushed?
Yes.
Yes. What?
What?
Can you give an example? Or? Anybody else? So we have yes and no. That's representative. No. So there's nothing that moves without being pushed. But I'd like, don't give me an answer based on something that you've heard before, but based on, you're a scientist and you're exploring the universe and you're looking around the phone.
If there were no powers, if there was a world, so we would just roll it from the middle and stop.
Did you ever see that?
No, but they say that.
Okay. Well, we're gonna. That's very good. Okay, but we're gonna not rely now on things that we heard or learned. Something we're scientists. We're now looking at phenomena, just at what we know. Okay. I mean, when they say it's something to test. If you hear something, say, well, they say that's such and such, but we tested in the laboratory. Okay. What do you think would happen if we tested in the laboratory? If we took something and moved it, rolled it, and took this chalk and rolled it. What happens? Besides falling off the table, right? It stops eventually. Okay, so things that move come to a stop. So it seems. Does that seem right to everybody? Or has anybody ever encountered something that moves by itself or in space? Okay, what moves by itself?
It doesn't stop.
Okay, how do you know? How do you know?
Stop.
They say. Okay, no, that's good. You're right. They say. Okay. You're correct, but I want to limit ourselves to what we can see. Okay. What? Anybody else? Is there anything that we do see sometimes that moves that we don't see something pushing? Can anybody think of any example? Is there an example like that? Or are you sure? The sun. Okay. Does the sun move? You know that? How do you know the sun is moving? Is the sun moving? Okay. How do we know the earth moves? So one of us is moving, or both of us are moving. Okay, so we don't. How would we know that the sun is moving? How do we know that? Everything is moving. What? Is this moving? It's moving. How do you know? Okay, you're right that the atoms are moving, but we certainly don't know that from looking at it. We can't see it. We wouldn't know. And for many years, people didn't know about it. Right? So they would say the Pluto's not moving. But in other words, if you look at things, basically it looks like things that are moving because something is pushing them, and things that are moving come to a stop. All right, about 500 years ago, all that changed, and one of the persons who was instrumental in changing that was Galileo. All right, we're not going to go into depth into what he discovered, how he discovered it, and so on. What he did is he used his imagination to think things through in a consistent way. He did experiments. Instead of just hypothesizing, he did some experiments and he found some interesting things. For example, let me ask you, I push this, what would you say? How far will it go? If I push it with a medium amount of force, let's say I'm going to push it now, what do you predict? How far will it go? 6 inches, okay. Obviously, what will it depend on? How far it will go will depend on what factors?
Friction.
How far I push it and?
Friction.
Okay, so now the question is, it comes to a stop. What could I do to make this go further with the same push? I'm going to exert the same push, but I want it to go further along the table. What could I possibly do to do that? Is there any way that I can do that, or is it a law of nature that when I push on it with this force, it's going to go, whatever, 6 inches? Okay, I can put some water on it, I can put some oil on it, and so on. Right, that would be the technical term, correct? I can put water or oil or something like that. I can do it on ice. Right, and our experience is that it would go further. So, in other words, it's not a law of nature that when you push on with this amount of force, it's going to come to a stop. It depends what the surfaces are. Now, if we use our imagination, we would say, well, let me imagine a surface that's smoother and smoother and smoother and smoother. What will happen? What is likely to happen? The more smooth I make the surfaces, and more oil I put, or a new kind of oil, and then yet a new kind of oil, or I make a ruler out of it, a special kind of material, what do you think might happen if I push it? It'll move further, right? It'll move 8 inches, it'll move 10 inches, it'll move 3 feet, it'll move 5 feet. So now the question becomes, if that's the case, can I find some materials that will make this move can I always improve this? Is there some limit to how far it'll move? No matter how I change materials, no matter what kind of oils I discover, no matter what kind of smooth ice I find, is there some natural law that says that it must come to a stop at some point? So we don't know. We don't know because we would have to do that experiment. Well, let's say we experiment and we find that the more I change the materials, the further it moves. It moves further, it moves 3 feet, and 5 feet, then it moves 10 feet, then I find some super new material, and it moves 50 feet, and then I find something extraordinary, it moves 100 feet, etc., etc. Do I assume that this will go on forever, and essentially, well, it's a strange assumption to make. We don't know which way to assume. All right? What Galileo did, to some degree, was make a wild leap of the imagination, a very creative idea. And he hypothesized, he said, objects do not stop on their own. They only stop if there's something stopping them. Just like something will move only if something is moving them, something stops only if something is stopping them. Now what's stopping this? Nobody stops it. Why does it stop? Well, we call it friction. We know that if we put oil here or ice or so on, it stops less, right? So we call the amount of stopping, we call that friction. Okay, it's just a word. But why is there friction? I mean, why should something stop?
There's a force that pulls it.
Okay, by definition, if it's stopping it, we call it a force. Okay, that doesn't explain. It's the word. Okay, you know when you rub your hands, what happens if you rub your hands quickly? What do you feel? Heat. Okay? What's happening are the molecules in the edge of your skin over here are rubbing against the molecules at the edge of your skin over here. And that rubbing, intense rubbing, gives off heat. You're expending energy and it's coming out as heat. Okay? But there's definite, you can feel they're rubbing against each other. And that's clearly going to slow something down. Now why is this is not rubbing, it's not rubbing hands. Why is this rubbing against the table? Is it rubbing against the table? Why would this be rubbing against the table? I mean, I don't want it to rub against the table. Why is it, I can move my hands so they don't rub against each other.
Gravity.
Okay, yeah. Okay, right. I don't want to get, all right, you're saying gravity, what does gravity have to do with it?
Force the earth that gravity that holds things on the surface.
Right. Okay, so the gravity of the earth is just like it's holding you down, it's holding this down. So when I push this, it's not just moving like this. Gravity is pulling it down. It's pulling it down the whole time. So it's going to rub against the table. Okay? Well, I don't want to use the technical terms until we define them. We'll just talk about what we can see, and then we'll define terms like force and direction. Okay? So we see that because there's gravity, that we know. We don't have to be told about that. We feel the gravity. We know that there's gravity pulling this, right? We can see it. It's pulling it down. When you try to pick it up, it's hard to pick it up. All right? So clearly, this is pushing against the table. So when I push it sideways, it's going to rub against the table in the same way that my hands rub against each other. And that's what causes it to come to a stop. So I theorize that if I make this less and less, and I give that a name friction, if I make that friction less and less, then it should have less and less resistance to the motion and should go further from me. And then I can say, well, one second. If there were a frictionless surface, now maybe there can't be such a thing as a frictionless surface. So I say, if there were a frictionless surface, it would move forever. But maybe there can't be such a thing. So what do I say instead? I say that motion itself will continue forever in terms of the motion. But because the constraints of nature are that there's always some kind of surface and there's always friction, so it will eventually come to a stop. But it's not that the motion itself wants to stop or has to stop. It's just something is stopping it. Not that the law is that things have to stop. Just that there's always something there. So now, is there a situation where there might not be something there? Okay, in space, in a vacuum, right? Where if there's nothing there, you're far away from any planet. All right? In theory, if you moved something, there's nothing there to stop it from moving. It should just go on and on and on and on and on. Now that's not something that we could have tested before we actually went out to space. Okay? So you're getting a little bit of a taste of how the scientist approaches just natural phenomena. You start out with looking around at the universe and trying to figure out what can we abstract out from what we see. Something very general, motion. Not just the motion of an individual thing, but motion in general. Then we look at motion and we try to figure out, well, how do things move? Why do they move? Why do they stop? Etc. Okay. This is Galileo's law of inertia, basically. That things will only move if you push them. If you push them, they continue moving as they were moving, unless something stops them. Okay. Newton's first law of motion. Every body continues in its state of rest or of uniform speed in a straight line unless acted on by a non-zero net force. Okay, by now, that should make a lot of sense to you. Non-zero net force, because obviously if there's two forces acting, they cancel each other, it's not going to work out. Okay. In a state of rest or of uniform speed in a straight line. No change of direction. Okay, this will be very, very clear to you.